We acknowledge the first Australians as the traditional custodians of the continent, whose culture is the oldest living culture in human history. We pay our respects to elders, past, present and emerging, and we respect their cultural heritage, beliefs and relationship with the land. We extend our respect to all Aboriginal and Torres Strait Islander people here today. They share the memories, traditions and hopes of the traditional ancestors with the new generations today and in the future. We would also like to thank them for looking after this land for thousands of years.
As my friend said, my name is Rusty. I'm here from Fizzics Education, and we're going to be talking about water today. Now, unfortunately, I'm not going to be talking about walking on water, although by the end of it, maybe we can figure out how we actually could walk on water. But you could see Karen before, you can see me now. There's actually another one of my friends that's with me today. Their name is Jackie. Jackie, did you want to say hi to everyone?
Hi everyone, this is Jackie. I am coming to you from Melbourne today, and I am a scientist like Rusty, except instead of doing experiments today, I will be on the Q&A answering some of your questions. And if I think one of your questions is really interesting, that lots of people would want to know the answer to, I will ask Rusty, hey Rusty, can you please answer this person's question?
Beautiful. So as Jackie mentioned, she's going to be looking through your questions and answers, trying to type out answers furiously. And if she sees a great question that thinks I should answer live on camera, she will pop that down. Now, friends, if you don't see your question answered straight away, it's because we're getting a lot of them through. So don't keep on repeating the same question and again, please. So we're going to be talking about water. And for those that haven't seen the Q&A button yet, down the bottom, you've got a little capital Q, a little ampersand, and a capital A. It stands for questions and answers. So you can ask questions by clicking on that and typing them out. Now, if I ask you a question, I might either get you to try and type the answer in there, or I might get you to use the raise hand button. So down the bottom of your screen, there's an option to raise hands. And we can see how many of you do raise your hands. Let's give that a test, my friends. Can we please use that raise hand button now? It looks like it was a pretty good success. Seems to be fluctuating a little bit. All righty, let's lower all of those hands. And then that way we can start talking about what I've got in front of me here. I've got some water. That's pretty important. I've also got a bunch of different things that we're going to be playing around with. And we're going to be learning about things like surface tension and buoyancy and all sorts of other fun terms. What I want to show you here is I've got two ping pong balls, or actually one's a ping pong ball and the other one is a cat's toy. They're both made out of plastic. If I put these in the water, I wonder which one's going to float. Let's find out. They both have about the same amount of plastic in it, but this one's even got more. Surely that one should have sunk if there's more plastic there. But it does not. Jackie, why do you think the pink one floats? Is it because it's pink?
I mean, that is definitely a difference, a variable. Maybe one is more dense than the other one, because I hear dense things sink and less dense things float.
I wonder by dense. I've been told I'm pretty dense, but I don't think it's the same thing. When we say density, we're talking about how much stuff is in there. And I've actually got a really cool example right here. I've got some water and I've got some oil, two different liquids, but the water with a bit of food coloring is more dense, and so it will sit down the bottom of this container. If I try and turn it over, well, they swap places. That water is always going to be down the bottom. If I try to mix them in together, they will mix for a bit, but they don't like to stay mixed. So they stay separate, and the water will eventually go down the bottom because it's more dense. It's got more stuff in the same amount of space. Another way I can show you about density is about this one here. I've got a liquid down the bottom. This is salt water. So it's water that's got salt dissolved in it, which means that it's got more stuff in the same space. Then I've got some beads. And then up the top, I've got a special type of alcohol that we find in things like hand sanitizer. Give this a bit of a shake. We're going to see something interesting happen. Those two liquids, well, they will mix together very temporarily, and together their density is in the middle. Now the blue beads are actually the most dense. The white beads are the least dense. But these two liquids, they don't like each other as well. So they're going to unmix, hopefully starting very soon. We're going to see the salt water move down towards the bottom. We're going to see that alcohol move towards the top, and those beads are going to start moving back together again as their density exchange. Hopefully it will happen soon. Come on, tap, tap. Sometimes it takes a little bit of time. So as we're waiting for that to go back, I'll bring your attention back to these two things. You might think that this is actually about density, but both of these are a similar sort of plastic. Oh, Jackie, we've got a question.
Well, just so everyone understands that I have seen them, a lot of our friends guessed that the pink one has holes. That's why it's different.
Ah, excellent. And they would be 100% correct. What we've got here is, instead of density, we've got another word that starts with D. It's displacement. The one with the holes allows water to go into the middle of it, and it can't push the water aside, whereas this one can. And it's actually the same reason why boats can actually float. So let's talk about what I've got here. I've got some plasticine, and at the moment it's just in a big ball. If I put this in, let me see. Let's use the raise hand button if you think this will float. Will this float? Oh, it's going up still. Okay, everyone lower your hands. And now use the raise hand button if you think it will sink. Seems like lots more people think it will sink. Let's find out. Yeah, it definitely sinks, because the density of this is much greater than the density of the water. It's heavier. But if we actually change the shape of this, and for this I need to get really strong and try and make it as flat as possible. It's a bit harder now because it's been in the cold water, but I want to try and make it without breaking any holes in it. I want to try and make it into a cup-like shape. This plasticine's a bit tough. All right, let's see if that is going to work. Now, I haven't made this any heavier, and let's see if I've made it big enough. And no, I did not. Let's try that again. And I've got, because I'm playing with water, I've got a nice little towel over here to try drying things out. With this, what we're trying to do is we want this shape to displace more water than it weighs. So the weight of the water it displaces needs to be greater than the weight of whatever we're trying to float. All right, let's try that. Let's see how we go. Oh, not cupped enough. Try and try and try. Maybe that one might work. There we go. We've got it floating. And it seems I did make a tiny little hole in there, because if I add a marble to it, we can get it all to sink. So let's actually try that with another material. I've actually got some foil here, and that's really, really light. So that will be much, much easier to make a boat. So let's put this off to the side just for a bit. Let's get some foil. And see if I can break it without tearing it too much. There we go. I'm going to make a boat shape out of this. So let's maybe go like that, maybe. Fold that in. Fold that in as well. And then we'll pop that out. Pop that out. There we go. We've got a boat shape. It's kind of like a boat. And that floats because it's pushing aside more water than it weighs. Even though it's made out of metal, it can still float. And this is actually how we get metal ships to actually float. Now, I've got a bunch of weight that we can add to our boat. And I'm going to start adding some marbles to it. While I'm adding marbles to it, I want you to pop down in Q&A how many you think it's going to take to sink this boat. Sorry, Jackie and Karen.
Just all right, numbers. We have 27, 21, 7, 5, 6.
So let's go 1,
10,
2, 3,
4, 22,
5,
3,
7, 8,
15,
9, 10, 11, 12.
Someone said all the marbles.
13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47. We just put all of them in. Oh. There were so many, I lost count. I think it was about close to 100. So if you were close to 100, good job, because you did really, really well. And that boat actually did pretty well. Better than I expected it would.
I just want you to know, Rusty.
Yeah.
1,200 responses, okay?
Yeah, sorry about that. I thought it would be funny. Maybe not as much as I thought. All right. So we now know how boats can actually float. What about some other things? I've got some other things here, and this is going to be going back to our other D word that we said before, density. I've got 2 Cokes. One is sugar, one is diet, which means it's sugar-free. Let's find out what happens when we put the one with sugar in it. It's down the bottom. It's sunk. Because this is more dense than the water, it can't displace as much as it weighs. Let's find out what happens with our diet. That's up the top. What's the difference between my diet Coke and my normal Coke? What is one missing that the other one has? Pop that down in Q&A. I'm sure we'll get spammed with a lot more answers for this one. Sorry, guys. What do we have as answers for that one?
Okay. Someone said sugar content. Must be
Yeah.
because of the sugar content that's making the difference. Everyone is saying sugar. Declan says the sugar one is more dense.
Yep, it absolutely is. Remember how this one here, I said there was salt in the water? Salt and sugar, well, they both dissolve. So that means you can get more stuff in the same space and it ends up being denser. And that's why we've got this one that sinks, whereas the sugar-free actually starts to float. Alrighty, let's move this one out and let's see what else we can do with some water. Well, I want to show you a couple other ways that we can make things float. And one is through something called surface tension. And the way I'm going to show that to you is just with a little tray of water and with some paper clips that I've got here. I need to get some of these out. Okay, we'll try with a few. Let's grab some of my water. Pop it in this container right here. Maybe a little bit more. And let's grab my camera so you can actually have a nice close look down at this. Let's change that one across. Here we go. All right. So if I just try and get a paper clip to float, let's see what happens. Not much, because the metal weighs more than the water around it. It can't displace very much. But if I very, very carefully, and hopefully I can get this one to work because it can be a bit tough, if I carefully place this in the water, I can get that to float. So let's try this again. Now, one of the reasons why I've made this little device is because my hand isn't disturbing the water next to it. It makes it nice and easy and repeatable. And we always love when things are repeatable in science. So this is floating because of the surface tension. On the top of the water, all of the little water molecules, well, they're holding each other's hands figuratively, and they don't like things to break through them and break them apart. So they are keeping these things afloat. And you've probably seen this before. If you've got a pool or you've been to a pond or a natural water hole, you might see little bugs that jump across on the surface of the water. And they use the surface tension with their legs to actually walk on water. So Karen, that is one way that you could walk on water, is using the surface tension, but you just have to be really, really light and the size of a bug. There is another way, and we'll get to that soon as well. All right, let's pop those down and they sink pretty easily. Now we're going to use surface tension again, and we're actually going to use something else to break it. So let me change my camera. I'm going to go to a top-down one this time. I've got my plate. I'm going to grab some water. I'll pop that in there. And then what I want to do is I'm going to pop some salt. Once again, because this is very light, this is going to go on the surface tension. And it's not going to sink. It's going to sit on top of the water. Next thing I'm going to do, though, is I've got some detergent, and I'm going to put a droplet right in the center. What do we think is going to happen? My friends, if you want to pop that in Q&A. Yeah.
Sorry, may I just say...
do you have a suggestion, Jackie?
I was just going to say, guys, if you are spamming in the Q&A so that I can't see people asking actual questions, this is the first warning. I will have to remove you from the webinar. So please do not spam the Q&A. Thank you.
Thank you for mentioning that, Jackie. Yes, friends, we're all here to have a good, fun time. So please be nice and respectful. All right. So if you think you might know what will happen when I put the detergent right here in the center, pop that down in Q&A. Just do it once, though. You don't need to spam it.
Lots of people are saying it will run away, it will separate, it's going to spread. Rusty, it's not the salt that you've put on there, though, right?
No, this was pepper that I put over the top.
Yeah, so everyone, it's pepper, not salt.
Otherwise, the salt would dissolve into the water. All right, let's find out what happens. And it's going to happen very quick. It all popped out. That's because soap and detergent is able to break the surface tension of water, and it stops those little water molecules from being able to connect to each other and attract each other like they're holding hands. So that means that when we break it in the middle, all of the water molecules, they suddenly pull out towards the side and they carry all of that pepper out along with it in each different direction. All righty, let's change back to my side camera, and we're going to do another experiment with some surface tension. We've actually got a few more, but I'm going to do this one with a little glass I've got upside down. We're going to go to this one here. Actually, we might go to the front one and zoom in.
While we do that, I thought we would answer an interesting question. Someone had asked if it's true that there's like 1 billion atoms in a drop of water.
Oh,
now,
that is a great question.
I did some maths, and in a single drop of water, there are 10 to the 21 drops,
so a lot
atoms.
More.
Yeah, so that's like 1,000 billion billion. So not just 1 billion, 1,000 billions of billions. That's how many atoms.
Now, I'm going to put some water into this one. And thank you for that awesome fact, Jackie. I really do appreciate that because I would not have been able to answer it. I'm going to put some water on top of this very soon. But to make it really easy to see, let's just pop some food coloring in here. And that way it should pop up against my blue jumper and against the green. So let's try this. So I've got my pipette. I'm going to start putting some droplets of water onto here. Now, oh, Jackie, should I do it? Should I ask how many droplets for our audience? How many they think?
How about we say, if you think it will take more than 20 drops, raise your hand. If you think it's less than 20 drops, don't raise your hand.
I think that's a much better option, Jackie. Good idea. Oh, we've got lots of people putting their hands up. Alrighty, I don't know if this is from a bit earlier, but I do see a bit of spamming going through on the Q&A.
Yeah, I've never done this before, but I am just about to kick someone. So please, everyone, be nice. Otherwise, other people won't be able to.
All right, let's start counting this out and let's see how we go. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. So we're up to 40. And if I zoom in a bit closer, you might start to see something really interesting happen. Oh, and turns out I can't actually zoom in closer than that. So where were we up to, Jackie? 40, I think.
Something like that.
Let's just say we are 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. And oh, we just got a little bit falling off. So what we had here is this little shape. It's called the meniscus. And that's from the surface tension of that water. All those little water molecules holding onto each other. And they will keep on doing it even when the water tries to escape, until eventually there's so much pressure from the water inside that it will actually jump out. Let's see if I can add some more.
Oh, it's pretty risky. Pretty risky, Rusty.
Then
there we go.
Gives way. Now I'm just going to dry that up, and I'm going to try this same experiment again, but this time I'm going to add a little bit of detergent to that water. And we'll see if it gets anywhere near the same amount. Actually, I don't even need to add it to the water. I can just add a little bit to there. Let's see how we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and it's already over the side before it even makes a meniscus. Let's see. Yep, down the side, and it just keeps on dripping off to the side, just because we added that little bit of detergent to the top of that one. All righty. We're going to play around back with buoyancy again, and we're going to make something called a Cartesian Diver. And to do this, I'm going to use a pen lid. Now, it's one that does not have a hole in the top. I'm going to use a bit of plasticine. We need a little bit off to the side. I've got another one that I've made previously using some different materials, but I'm going to show you how you can make one at home. We need a drink bottle, and we're going to fill that up with water. Let's zoom out just a little bit so we can see what's going on. There we go. What I want to do is I want to fill up my water bottle to start off with, and I want to make sure that there's no gaps in there. I want it to be all the way up to the top, totally full of water, no space up the top. Go. All right, next thing I want to do is I want to add a bit of plasticine to this, but I don't want it to sink all the way down. I just want it to be almost floating. So that was a bit too much. Let's take a little bit away. And that is just bobbing at the top. I might add a little bit of that back. And see if I can get it to sink just a little bit lower. That's pretty good. Maybe add a little bit more. Great thing with plasticine is you can add some away, take a little bit back. It is easy to do. Oh, I think that's probably a good amount. So we want it so it just starts to float. So I've got that all on there. And then I'm going to add this to my water bottle. We can see it in there. And then we're going to add probably a little bit more water. Just so that it's all the way up to the top. And then we're going to seal this in. Now, let's zoom back in again. And down a little bit. Hopefully, you might be able to see that guy in there. You can sort of see the black of the pen and the green of the Play-Doh. Now, at the moment, it's floating where it is because of its buoyancy. It has a gap in the cap that's got air in it, and that's displacing the water. And it's just enough weight on the bottom to pull it down to the level it's at. Let's see what happens if I squeeze this. It goes down. When I stop squeezing, it goes up. When I squeeze it, it goes down. And we can actually make it keep on going up and down. Now, the reason why this works is because when we squeeze on this bottle, we're increasing the pressure of the water inside. And because that cap is open on the bottom, when the water pressure increases, it pushes up into the gap and it compresses the air that's up there. And so because it's displacing less water, it starts to sink. And it's actually how real submarines work, or very similar. They don't have to increase the pressure of the water around them, but they can increase and decrease pressure of gas and canisters on board. Awesome. All righty, how are we going for time? We've got 10 more minutes, so we've got plenty of more time to do some more experiments. Do we have any more questions and answers coming through at the moment?
Here's a good one from Zach. Why can't we see molecules? Is it because they are so small?
Oh, that is a great. So you are right. It is because they're so small, but that's only sort of half the explanation. The only reason we can see things is because of light. For us to see something, we need visible light to bounce off it and then bounce back to our eyes. So at the moment, you can see me because I've got light above me that bounces off my face or my hair, and it bounces to this camera, which then goes through the internet to your computer screen, and that releases light, and that's what you see. If we were alive in the same room, you would just see the light that bounces straight off me. So we need visible light to actually see. But visible light, even though it is quite useful, it can't actually reflect off everything. It can only reflect off things that are really bigger than what we call its wavelength. So as light's moving through the air, it wiggles up and down, and each up and down, the length of that we call the wavelength. Visible light goes down to about 0.0005 or 4 millimeters. I think I got that right. I think, Jackie, maybe. It's, 0.0004 millimeters, which is about half a micrometer or about 400 nanometers. And this is the smallest thing that we can actually see with light. If anything smaller than that, we need to go to something called an electron microscope, and they can see down to much smaller than that. But to see atoms, we have to use things called atomic force microscopes. And they're kind of like record players where they've got a little needle and they drag it along a surface. And as it's going up and down across the surface, we can actually measure the height of things by shining a laser off the top. A very, very complex sort of thing.
Rusty, we had a question. It went past so quickly, but someone did want to know, if you got your Cartesian Diver bottle and you shook it up, what would happen to the little diver?
Oh, that is a great question. Let's find out. Well, let me seal a little bit better. It sunk. I think what I've done is we'll find that there's no longer any air in there, because I probably managed to turn the Cartesian Diver upside down, and the air that was inside that guy is now probably, if I turn this upside down, there we go. It is just right there. So now it's no longer inside that guy. It will not float again for me, unfortunately. If I tried to do it with this one, I don't think this one would have any trouble with it. That was a really good question. Let's see if it works with this one. So that one goes up and down. And with that one, I managed to get it stuck halfway. There we go. And it's still floating in there. I can go up and down.
I think this is a rather philosophical question from Emily. What would happen if there was no molecules in water? Would it still be water?
Well, that is a great question. Well, we could still call it water, but it wouldn't meet our definition of what we now call water. Water is a molecule with 3 atoms in it, 2 hydrogens and 1 oxygen. That's what we've decided to call water, or water is what we've decided to call that molecule. If there wasn't any molecules or any atoms at all, well, we've actually already got a name for that. We call that a vacuum. And that means when there's nothing there, that's a vacuum. And that's the name that we've given it. But these are just names that humans have made up at some time in the past. So we could call it anything that we want. Those are just the names that we've decided to all call them together. All righty, let's do a little experiment with a boat. Do we have another question or no?
We have so many questions, but we should probably do our demos first.
Let's do another experiment and then we'll come back for some questions. I've got a big thing of water right here. I'm going to open up my camera so we can actually have a close look over the lid. Let's change this one across. And we want that one there. All right, let's move back just a little bit. There we go. Now I've got a boat that I've made and I've got a little U in the back. What I'm going to do is I'm going to pop that in my water. And in a moment, I'm going to put some detergent on the back of that boat. Let's see what's going to happen. Now, does it still work if I put it this way? No, it doesn't work anymore. Because once we put that first little bit of detergent in there, it actually breaks that surface tension for all of the water. Just a little bit of detergent goes a long way in this case. And when we had it over this side to start off with, we were breaking the surface tension behind it. So the surface tension in front of the boat was pulling it forward towards the camera. Now, I just saw the Q&A amount. That is a huge amount of questions or answers maybe to my questions. All right, let's go back to here. And let's talk a bit about where we actually use detergent normally. We would use it in the kitchen. And it's because we're trying to wash away things like fat and oils from our foods on our plates, or maybe we might use it in our detergent for our laundry to wash off oils and sweat from our body, from our clothes. And we usually use water to wash it away. Now, I've got water and oil here, and we can see that even if I try and mix them with a bit of agitation or hand mixing, they mix for a bit, but they don't like to stay that way, and they'll start to separate out. So that's why we actually use detergent, because it breaks down the surface tension and allows things like fats and oils to mix with water, or rather water to mix with fats and oils. And that allows us to use water to wash our plates, our clothes, our hands, all sorts of things like that. All right, looks like we've only got a few minutes left. Maybe we might do some Q and answers.
I like this one. How does water make things rust and not other liquids?
Oh, that's an interesting question, especially because I've actually got a little bit of rust in here from some of my paper clips. Now, it all has to do with the shape of water and how it's got charge on each side. So it's all to do with something that scientists call galvanic series. And it's actually part of the reason why batteries work as well. So you get oxidization of one material, you've got oxygen, you've got electrons coming off. It's a really complex process, probably a little bit too complex for me to go too much into detail, but it has to do with things like an electrical charge. So things like when you've got salt in water makes things rust much, much faster, because that helps etch things away. And it actually rusts away faster if you've got two different types of metal next to each other. So if there's two bits of metal connected, like in a screw and a bolt, and they're not the same metal, that will actually make one rust away much, much faster.
All right, Rusty, you ready for a speed round of questions?
Yeah, let's do it.
Cool. All right, Poppy wants to know, why do you drink fresh water and not salt water?
That's actually a great one. So we drink fresh water instead of salt is because on the inside of our bodies, our cells have certain types of salt on the inside. And if we were to have too much salt external, through osmosis, we could actually change the water content of our cells. So it actually helps dehydrate our cells if we drink salt water.
We have another question. Why does it hurt so much when you slap water, even though it's a liquid?
That's great. It's because of the surface tension that we mentioned before, as well as its density. It's quite a dense material, but it's surface tension. That's why maybe if you've ever watched people diving at the Olympics, they don't just dive straight into water. They actually usually have like a sprinkler going on the surface, because it breaks down that surface tension, so it hurts the diver less when they go into the water.
Okay, last question, because we're desperately short on time. Lots of people are asking questions about atoms touching. So if atoms are not actually touching each other, are we ever really touching anything? Because we're made of atoms, right?
That is a great question. It's one of those ones that is like a mind explosion. And the answer is no, we are not ever touching anything. We have never touched anything, and we will never, ever touch anything. You might think that you're sitting on that chair, but you're actually hovering slightly above it. Too small of an amount to actually see, but the electrons in your bottom are repelling the electrons in the chair, and you never touch it. You might think that I'm touching this table, but the electrons in my hand are repelling the electrons in the table. So it's kind of sad.